Welcome back to Standing on the Shoulder of Giants. When Carl Yancey first discovered star noise, he had trouble getting astronomers to pay attention. He wasn't an astronomer himself. He was a physicist and engineer at Bell Labs in New Jersey, working on designing a new antenna that could detect long wavelength radio waves. His antenna was enormous, 100 feet across and 20 feet tall. When Yancey began using it, he quickly discerned that he could detect static produced by thunderstorms or something else, a faint but constant hiss in his data. That something else ultimately proved to be radio waves emitted by the center of the Milky Way, a discovery he reported in 1933. It was a phenomenal finding, the first clear detection of radio emissions from space. Still, he had trouble obtaining support to explore his discovery further. The country was in the midst of the Great Depression. Astronomers didn't work with radio detectors, and they were hesitant to sink limited funds into a brand new endeavor. Bell Labs also couldn't justify funding a project that wasn't directly related to their main goal of long-distance communication. It wasn't until several years later that an engineer named Grote Reber built the first dedicated radio telescope, a parabolic 31-foot dish in his backyard, and began surveying the sky for signs of astronomical radio waves. Today, more than 80 years later, radio astronomy is an immense field that has given rise to enormous radio dishes, planet-wide arrays of telescopes, and some of the most exciting scientific discoveries of the last century. Radio waves lie at one extreme of the electromagnetic spectrum, with low energies and long lengths. Most of the telescopes we have discussed so far in these programs utilize visible light, with wavelengths of only a few hundred nanometers. By comparison, the shortest radio lengths are a millimeter, and the longest wavelengths that we can detect are tens of thousands of kilometers. As we move from one end of the electromagnetic spectrum to the other, we can use different wavelengths of light to probe different physical phenomena. When Carl Yancey first detected radio waves with his Bell Labs antenna in the early 1930s and pinpointed their location, he thought he was detecting radiation from the sun. However, as he continued to follow the signal for months, he noticed that the most intense source of this signal was sliding away from the sun's location, following the motion of background stars across the sky rather than the motion of the sun. He compared his signal's location with astronomical maps and realized that his signal was coming from the Milky Way itself, and was strongest near the constellation of Sagittarius, which lay in the direction of the Milky Way's center. Yancey didn't realize at the time, but he was detecting a signature of our Milky Way's magnetic field. Our galaxy's magnetic field is thousands of times weaker than our own planet's, but astronomers today believe that it impacts how stars form in our galaxy, along with the flux of strange particles known as cosmic rays. Cosmic rays are high-energy protons, atomic nuclei, and solitary electrons streaking through space at close to the speed of light. Even today, astronomers still don't fully understand where cosmic rays come from. Still, we do know that when cosmic ray electrons travel through our Milky Way, they can be slowed down a bit as they follow the curves of our galaxy's magnetic field lines. To slow down, these electrons must release a small amount of energy in the form of low-energy light, radio light. This radio light was what Yancey detected emitting from the entire Milky Way and appearing the most intense or brightest near the galactic center, where the magnetic field is the strongest. In the 1930s, Yancey's discovery was met with scientific curiosity, but not much else. His antenna was the only one of its kind at the time. Observatories weren't building radio antennae, and the very idea of a radio telescope was foreign to most astronomers. The antenna itself also looked decidedly unlike a telescope. It looked more like a gigantic version of the radio arrows you may have seen on cars, an ungainly array of straight-line antennae arranged in a series of squares. A crucial decision made by Yankski when designing his antenna was to mount it on a set of Model T tyres, allowing him to spin the antenna in a complete circle. This mounting led his colleagues to nickname the antenna Yankski's merry-go-round. But ridicule aside, it allowed him to put a detector wherever he wanted and hone in on precisely where the signal was coming from, including the centre of the galaxy. It was effective and the discovery was intriguing, but observatories weren't exactly lining up to build more antenna. Today, Karl Yankski is recognized as the founder of radio astronomy. The National Radio Astronomy Observatory grants a postdoctoral research fellowship named in his honor, and even the physical unit used to describe brightness in the radio astronomy is named after him, the Yankski. Still, it took another radio enthusiast and engineer, Grote Reber, to design what we recognize today as a radio telescope and begin the field of radio astronomy in earnest. Grote Reber was 21 years old when he first read about Yankski's discovery in 1933. An electrical engineer by training and an amateur radio operator, Reber immediately got excited at the possibility of what Yankski described as electrical disturbances of apparently extraterrestrial origin, and vowed to devote his career to this exciting brand new field of radio astronomy. However, when he applied to work at Bell Labs, he was turned away. The company had no job openings in the midst of the Great Depression. Disappointed but not discouraged, Reber set about building his own radio telescope in his backyard. Completed in 1937, Reber's telescope had a parabolic 31-foot dish and a radio receiver mounted directly above it. In 1938 he successfully reproduced Yankski's observation of radio waves from the Milky Way. He went on to begin publishing the Astrophysical Journal, and then undertook the first radio-length survey of the sky. His published research finally kicked off a surge of interest in radio astronomy, and soon observatories were building radio telescopes of their own. Grote Reber's antenna may look a bit more recognizable than Karl Yankski's, but radio telescopes may still look decidedly odd to someone used to thinking of telescopes as having shiny glass mirrors. Most of them aren't ensconced in protective domes, and while there's at least a parabolic dish that sounds at least vaguely similar to the parabolic primary mirrors of telescopes like the Hale 200-inch at Palomar, radio telescopes still look less like shiny reflective surfaces and more like giant metal bowls. The trick comes when you remember that we're looking at radio telescopes with our human visible light detecting eyes. At the long wavelengths of radio light invisible to our eyes, the metal surfaces of radio telescopes are shiny. Radio waves pouring down from the sky will bounce off a parabolic radio dish and get focused into a receiver in the same way that visible light will get bounced off a traditional mirror and focused into an eyepiece or camera. Radio telescopes also follow the same basic optical principles as visible light telescopes. Making these telescopes big is still valuable. We may be working with much longer wavelengths, but the basic physics of astronomy still applies. If a telescope has a large collecting area, we can gather more light from faint and distant objects, and if a telescope has a large diameter, we can capture increasingly sharper images of the night sky. Fortunately, although still challenging, when it comes to building enormous radio telescopes, it is at least a bit easier. You don't need a massive glass blank for a mirror. Instead, you can use thin sheets of metal to fashion a dish. Second, the precision of the dish doesn't need to be quite as unforgivably perfect. Recall that George Ellery Hale's enormous mirrors and the ill-fated mirror on board the Hubble Space Telescope had to be ground to a precision that was within 5% the size of the wavelengths they hoped to focus, giving them margins of error that were mere nanometers in size if they hoped to focus the 400 to 700 nanometer lengths of visible light. Now, remember that even the shortest radio lengths are around 1 millimeter, or 1,000,000 nanometers. Many radio telescopes working at longer wavelengths have a margin of error in their dishes that can be as long as a few millimeters. It doesn't sound like much, but it means that under supervision and working carefully, radio telescopes can actually be walked on. Radio telescopes can also observe through all sorts of weather. They can operate day and night since the sun doesn't emit much light in the radio frequency, and continue to capture data even through clouds, fog, rain and snowstorms. At some radio telescopes, snow will accumulate in the bowl of the dish, and it's most easily cleared by sending an astronomer out onto the dish with a broom. Imagine George Hale letting snow fall onto his 200-inch telescope and then sending a member of staff with a broom to stroll across the mirror. The difference in engineering have made it possible to build some truly enormous radio telescopes. The largest fully steerable radio telescopes in the world is the 100-meter Robert C. Baird Greenbank telescope, built in eastern West Virginia. The telescope is named after the West Virginia senator for good reason. It was Senator Baird who acquired the funding for the project, which was needed to replace a similar telescope, the Greenbank 300-foot, that operated successfully for years before suffering a sudden and catastrophic collapse in 1988. A 100-meter telescope is already astounding, but radio telescopes can get larger still. One of the biggest and most famous was the Arecibo Observatory, with a dish 1,000 feet across, built into the natural topography of a sinkhole in Puerto Rico. Since the dish is built right on the ground, Arecibo could not turn and point like a typical telescope. But by tipping its enormous receiver hanging 500 feet above the dish, it can focus on and observe objects that pass overhead. It might be tempting, looking at the large telescopes and 24-hour observing capabilities, to think of radio astronomy as easy. In truth, radio observations are some of the most technically challenging in all of astronomy, and effectively operating radio telescopes and detecting signals from space can be a tricky and delicate proposition. The difficulty comes when considering what radio telescopes calls noise. We already know that radio telescopes have different definitions of what we might consider a shiny mirror or a perfect parabola. As it turns out, radio telescopes also have a different definition of what we could consider dark. Most visible light telescopes operate at night for obvious reasons. During the day, the blinding light of the sun overwhelms the light of everything else in the sky, making it nearly impossible to detect the much fainter data from background stars or planets. Radio telescopes require darkness as well, but at very different wavelengths. Imagine that your eyes could suddenly detect radio light instead of visible light. Look around the room where you are sitting. In the radio spectrum, that room would likely be a blinding mess of strange and messy signals. You'll see a messy cloud of wireless networks, sporadic bursts of signals from nearby cell phones, maybe the occasional flash of a nearby microwave, or little blinks from the ignition sparks generated in the petrol-powered engines of cars driving past. Even fluorescent lights would show up to your new radio-sensitive eyes, emitting faint radio signals that could interfere with you perceiving the environment. To pick up faint background signals from space, radio telescopes need to be protected from this mess of contaminating radio light sources. but this can be difficult since the walls of a typical observatory dome or buildings aren't able to stop radio light. Instead, radio telescopes are placed in remote corners of the planet, not unlike the world's best visible light telescopes. Many observatories keep radio and optical telescopes on the same mountain tops for this very reason. Entire ranges of radio wavelengths are also protected by international regulations, restricting them from commercial or military use, so that no earthborne signals will interfere with radio astronomers' science. Some places like Greenbank, West Virginia, go even further. This part of the United States is designated as the National Radio Quiet Zone, with restrictions on the technology used by residents and visitors in an attempt to keep terrestrial radio signals as quiet as possible. People living within a 20-mile radius of the observatory aren't allowed to use cell phones or Wi-Fi networks. Microwave ovens are banned, and even cars run on diesel engines to prevent those small radio signals from spark plugs. It may seem extreme, but radio telescopes have been fooled before, detecting light that was originally thought to come from deep space, but was later traced to on-site microwaves, the odd cell phone or communication equipment from an aircraft passing overhead. We know that it's possible to make very large radio telescope dishes. In truth, we can build even larger radio observatories if we get a bit creative and think back to the two main perks of large telescopes. A large telescope area, like a big dish, will allow us to gather more light from faint objects. At the same time, a larger diameter is key to producing very sharp images. This is why large telephoto camera lenses are capable of capturing incredibly clear pictures of faraway subjects. We often want to accomplish something similar with telescopes, resolving individual stars in distant galaxies, or discerning the exact shape of a nebula or supernova remnant. With radio telescopes we can achieve incredibly large diameters thanks to a technique known as interferometry. Imagine that you have an array of several radio dishes, separated by as little as a few feet, or as much as a few thousand miles. You can picture those individual radio dishes as shiny spots, spread across a giant virtual mirror. When combined, the dishes simulate the size of a single and incredibly large mirror. If all of these dishes are pointed at the same object, they can record data from that object and then combine the data using a mathematical signal processing technique known as aperture synthesis to capture and produce a final image, depicting what we'd see with radio-sensitive eyes. This type of setup is known as an interferometer, an instrument that combines multiple sources of light. Radio telescopes like these can combine data detected from multiple dishes to function as a single enormous telescope. While each telescope dish still only collects a small amount of light, the results combine into a beautifully sharp and clear picture. The technique is much easier to describe than it is to execute. Interferometry is computationally complex, made easier at longer wavelengths but still incredibly challenging for radio telescopes. Radio interferometry makes it possible to build extremely powerful telescope arrays. One of the most famous is the Very Large Array, or VLA, in New Mexico. Originally built in the 1970s, the VLA consists of 27 dishes arranged in a giant Y. Each dish is 82 feet across and designed to be moved along a set of railroad tracks by a specially designed truck, increasing or decreasing the length of each arm in the Y. The result is a telescope that can actively change its size, with arms that can extend up to 22 miles long to simulate an enormous telescope. Even larger radio interferometers operate across the globe. These include the Very Long Baseline Array, with antenna stretching from Hawaii in the west to the US Virgin Islands in the east, to form an effective telescope the size of North America, and the Event Horizon Telescope, with telescopes ranging from Greenland to the South Pole, to create a planet-wide telescope. The Event Horizon Telescope made headlines in 2019 when it captured the first ever picture of a black hole. From their earliest incarnation in the 1930s to the cutting-edge telescopes of today, radio telescopes have continually made incredible discoveries. During its decades of operation, the VLA has made discoveries ranging from ice on the surface of Mercury, spotted by detecting radio light bouncing off the planet by a powerful radar system in California, to the birth of a planetary system, where the VLA's enormous size allowed it to see tiny gaps in a disk around a young star traced by fledgling planets in the early stages of their formation. In 2012 the VLA was renamed. It's now known as the Carl G. Jansky Very Large Array. A small radio telescope in England detected the pulsing signal that became humanity's first observation of a neutron star, and the planet-sized Event Horizon Telescope captured a photograph of a black hole, two discoveries that we'll be talking about in later programs. One astonishing discovery from radio telescopes came from early all-sky radio surveys, following the tradition established by Grote-Reber in the 1930s. A 1959 survey of radio sources, done using a radio interferometer west of Cambridge, England, detected two radio sources, 3C48 and 3C273, that appeared bright in the radio spectrum, but which had no visible light counterparts. Follow-up observations with other radio telescopes proved that these objects appeared to be surprisingly tiny, compact and bright. This finding puzzled visible light astronomers, who promptly set about to explain why maps of the radio sky and visible sky don't seem to match. In 1960, astronomers Alan Sandage and Thomas Matthews thought they had honed in on one of the radio light sources. They discovered what appeared to be a faint blue star at the same location, although to their surprise the star spectrum looked unlike any they had ever seen before, with strong broad emission lines rather than the usual neat absorption lines used to classify stars. Puzzled, the objects gained the nickname quasars, an amalgam of their description as quasi-stellar radio sources. Most astronomers suspected that these sources weren't really stars at all, but couldn't sort out what exactly they were. A breakthrough came a few years later in late 1962, when astronomer Martin Schmidt managed to capture a visible light spectrum of quasar 3C273 using the Palomar 20-inch telescope. To his astonishment, Schmidt measured an immense redshift for the quasar, corresponding to a distance of more than 2 billion light-years. His discovery eventually revealed that 3C273 and other quasars discovered since were actually an incredibly luminous nuclei of very distant galaxies. Each of these galaxies had a supermassive black hole in its center, with a total mass of millions or even billions of stars. These black holes were swallowing gas in these galaxies' centers at astonishing rates, and as the gas poured into the black hole, it was releasing large amounts of energy as electromagnetic radiation, making these galaxies some of the most luminous objects in the universe. Their luminosity made them radio loud, leading to their discovery in the radio surveys of the 1950s. If they hadn't been marked as unusual radio objects, they may have escaped astronomers' notice for many more years. Today, large radio telescopes continue making amazing scientific discoveries. Single dishes and interferometers all over the world are spending days and nights studying our own solar system. The birth of new planets and stars, the fading remnants of supernova, and the distant blasts of radio light from the luminous gas disks around supermassive black holes. All of these discoveries can ultimately be traced back to this first faint hiss discovered by Karl Jansky, and sparking the curiosity of groped Reber, which began the first century of humanity's study of the radio sky. Radio astronomy, as it turned out, had a particularly auspicious beginning. Jansky's discovery during his time at Bell Labs may have been the first surprisingly exciting faint hiss in the field of radio astronomy, but as we'll learn in the next program, it would not be the last.